Um, let's start now. So thank you for coming, everyone, and welcome to the 13th in our series, Tunneling in QFT. Yeah, thank you very much for joining. We have some more coming up. In April, we have Thomas Steingasser, and in May, we have Matthew Johnson. The March slot is currently free, so if you'd like to suggest yourself, please feel free to come forward, send us an email. But today we have Matthias Carosi, who's at Technical University of Munich, talking to us about false vacuum decay beyond the quadratic approximation. And yeah, very much looking forward to this. It looks like an important work. And yeah, please take it away, Matthias.
Thank you, Oliver. Thank you for having me, for the introduction. So good afternoon, everyone. Exactly. So the talk I will do today is based mostly on this work that came out at the end of November with my supervisor, Björn Galbrecht. I mean, today I will try to give a little bit of the motivation for why we went in this endeavor, into this endeavor, and maybe also a little bit of technical details. Please feel free to ask questions if some things are not clear during the talk as well. So exactly, this is a small outline of the talk. So we're going to be talking about stability of the standard model as a motivation, this for the framework that we will be looking at in the second part of the talk. Very well, so let's dive in. So, I mean, we know that the standard model contains a scalar, the Higgs field, and therefore it becomes an interesting question to ask ourselves whether the current minimum in which the Higgs field is sitting is indeed the absolute minimum. This is a very old question, even before the actual discovery of the Higgs boson. People were already looking at this thing, at this problem. So there are three scenarios once we compute the effective potential of the Higgs. I mean, here I'm talking about zero temperature effective potential, so basically including the quantum corrections of the most relevant fields in the standard model. Usually these are, for example, the top quark and the weak gauge bosons. And as I said, once the effective potential is computed, we usually distinguish three scenarios. Let's say most amenable scenario is the one in which the Higgs, the current minimum, is actually a stable minimum. So we say in this case that the standard model is stable, meaning that the Higgs is going to stay there for the rest of eternity, and that's not going anywhere. But there's also the possibility that this is actually not the deeper minimum of the effective potential, but there might be some other minimum. And therefore, there are two more scenarios. So another scenario in which there is another minimum for the potential. So eventually, because of quantum fluctuations and tunneling, which is what we discuss here most every month, eventually the field will tunnel and go there. However, we say this scenario to be metastable if the likelihood that this is going to happen is very low, meaning that compared to that eventually it will happen, but it will happen on such a long time scale that it doesn't really bother us, or it doesn't conflict with current data at least. But there's also a scenario in which is unstable, meaning that, for example, the barrier between the minimum and like the absolute minimum is very, very small, or it's this absolute minimum is very close in energy scales. But anyways, something that makes the rate at which this decay would happen so high that it's basically incompatible with our data, and our data meaning the fact that we exist and we observe a minimum of the Higgs at around 250 GeV. Now, with the current or most recent or most updated theoretical calculations, also using experimental data. This is, for example, a plot taken from work of Andreasen, Frost, and Schwarz from 2018. It seems that the values of the Higgs mass and the top mass as measured would state basically that the standard model sits in a rather narrow slit of metastability. And I mean, in these plots, for example, they also show some uncertainty ellipses that come basically mostly from uncertainty on these masses plus uncertainty on the alpha strong. But it seems that we're pretty definitely in the metastability range. However, exactly for this reason, it becomes very important to assess with a certain accuracy, to compute with a certain accuracy this decay rate. Most importantly, because if we were to find that, say, we would be in the unstable region, then definitely this means that new physics would be required to stabilize the Higgs at our scales. Now, I will therefore go a little bit into what we actually, what people actually do when they say they compute the decay rate of the Higgs at 0 temperature. Now, once we look at the effective potential of the Higgs for very high value of the Higgs field, of the field itself, it can be written as in 1.1. So this is basically a potential unbounded from below. In 4 dimension, this is also scale invariant. And de facto, we usually, then people usually work with a lambda that is basically a constant and kind of set the value at which this RG running coupling is computed at the scale that it's supposed to dominate the decay process. We're going to go back to the scale because this is a central question of the topic. And this is usually very, very large. With, I think, the calculations that I'm aware of for the effective potential of the Higgs, including two-loop effects and three-loop running and so on and so forth, the absolute minimum of the Higgs should be located at just a few orders of magnitude below the Planck scale. So we are talking about many orders of magnitude above, for example, the scale of the current Higgs minimum and the current Higgs mass. So for all practical purposes, the mass of the Higgs is just neglected at this stage. And this is usually the potential used for calculations of the decay rate. Now, once this is once we've set this picture, then basically the question becomes, what is the likelihood or the decay rate of a state sitting on the top of this hill, which is also a well-posed question, regardless of whether the potential we're taking is unbounded from below or not. And this, as I said, has actually a long history. In 79 already, there's this famous paper in which the authors were already using the stability question as a way to bound the possible Higgs mass and the top mass. But this was also developed by many, many others. So this is definitely not an exhaustive list. I just put a few time marks that I consider important spots, at least in the history of this research, or at least the ones I know of. And specifically, then we're going to mention the work by Isidori in 2001 and Russell in 2018 as starting point of what I'm going to discuss today. So exactly, now that we've set the stage, I want to talk about the fact of why is this hard? I mean, a priori, we know how to compute decay rates at 0 temperatures for a lot of theories. So why should this model be somewhat more complicated? And the issue is really, so to understand the issue, I will just start again from the formula for the decay rate. I mean, I wrote it here in terms of effective actions because this is going to be useful for what comes next. But really here, the decay rate per unit volume, is just given by this exponentiation of the difference of the effective actions in the bounce background, the usual Coleman bounce for vacuum decay, and in the Volkswagen background. And then there's some Jacobian factor for translations that come in front. I will also comment about it in a sec. And then basically, okay, just to convince you, maybe because in this form you might have not seen it that often, that this is nothing else than at least in some limit, it's nothing else than the usual formula. If we, for example, as the action, we choose to use the one loop, one PI effective action, which is a rather natural choice. It's basically the next obvious choice after taking the 3-level action. Then we find the usual formula with a fluctuation determinant here as the prefactor that encodes basically the fluctuations, and then the exponentiation of the difference of the classical actions of the bounce and the Volkswagen. Also, as per usual, I will also denote with a prime the fact that the translational zero mode are taken away from the evaluation of the determinant. And I should mention now that this is basically, or for example, for the traces, and this is all, I mean, eventually I will not write it anymore, but in all expressions that I write, we always assume or like that a specific procedure has been carried on so that the translational zero mode are not propagating degrees of freedom of the fluctuations around the bounds background. And this is also very relevant. Okay, so once we have set this out, it's important to address the question of zero modes, as I said. So we go back to this translational Jacobian. So what is the story? The story is that we have some symmetries of my theory. And the solution that I pick, in this case, the bound solution, breaks some of these symmetries. For any theory that we start with, usually we consider translational symmetric theories. So the bounds, which basically makes some point in Euclidean space more special than the other points, clearly breaks this, and this results in a zero mode of the fluctuation operator. I should say result in a fact that the solution is actually a four-parameter, d-parameter family of solution, where d are the d coordinates of x0, the center of the bounds, and for each of those d parameters, we have a zero node. And this is basically just depicted by the fact that if we have a bounce that is centered at x0, we can shift it and put it somewhere else in x1, and this is still a solution of the equation of motion, and it also has the same action. Now, this means that in general, we don't want to integrate over when we integrate over fluctuations, we don't really want to integrate over the fluctuation in the direction of the zero mode, but we should rather use what is called the method of collective coordinates that you might have heard already, which basically means we just trade, instead of integrating in this field direction, we integrate over the parameter. So the modulus of my solution. And in this case, we have d of them, as I said, the d coordinates of the center of the bounds. And then in doing this transformation for going from field space to moduli or to collective coordinates, we get a Jacobian. So I just called it JTR for translations. And we have d of them again, because we have d of these coordinates. And the integration just gives us a factor that is the volume of the Euclidean space. So I just split it into beta, which will be my time direction, and this curly v, which is the spatial volume, which makes it such that indeed we really only compute decay rates per unit spatial volumes and never full probability. So because we take basically space to be infinite. Now, however, as I told you before, in the case of the standard model stability, we usually work with a potential that actually exhibits at the classical level scale invariance, which means that when I look at the classical equation of motion given just by S prime of the configuration equals 0, I have an additional parameter characterizing my family of solutions, which is we're going to call R, namely the radius of the bounds. And this is, once again, a parameter that I can change. So for example, I can have a bounce of radius r. This is kind of like a two-niche depiction of a bounce in d-dimensional space, Euclidean space. And then if I dilate it, so I make it bigger and give it another radius, for example, r prime, this still solves the classical equation of motion. And this implies the existence of an additional zero mode, which is when basically I take the derivative with respect to this additional modulus. Now, so far, fine. This also happens in other realms of physics. We have, for example, also in Yang-Mills, PPST instantons or scale invariant. And then we can just trade it once again for collective coordinates. The issue is that in this case, if we do so, we end up finding that the integral over our collective coordinates, meaning the radius of the bounds, would actually give infinity. The reason is that this Jacobian is basically a constant, and actually I should mention there's an additional problem that this constant is actually infinity itself in d equals 4. So we have two infinities. We have the Jacobian being infinite in d equals 4, and we also have that even if we regularize it in some way, we still have the issue that the integral over the collective coordinate blows up for very large bounces. So we have an IR divergence, because the very, very large, so very, very infrared instantons are the ones that are making our integral problematic. Now, there is an old idea that is the obvious idea, maybe to anyone doing quantum field theory, that would be, well, the classical scale invariant, does not survive quantum corrections. Okay, this is not a conformal theory. Once we include quantum corrections, the scale invariance should go away. And so if we have a way of doing that, we don't even need to introduce these collective coordinates, or in a way, if you want, we can introduce it, but instead of integrating a constant over an infinite interval, we expect that whatever is the integrand of this integral should pick up an R dependence that is induced by my quantum corrections, such that that integral is made convergent. Now, this is, for example, what led to one approach, which is basically understand that whatever these quantum corrections are, they should basically cancel order by order the renormalization scale dependence of my classical action once I let my couplings run. And this induces some R dependence in the integrand. So this is, for example, what Isidori Ridolfi Astrumia did in 2001. And to my knowledge, they computed for the first time to next to leading order the decay rate of this theory. And what they do, I mean, they don't really mention the Jacobian problem, but basically what they do to get rid of the infrared problem is that they again do this RG argument for picking up the dominant radius and basically localize what would be the R integral to the critical radius. Now. The idea was further refined and made, if you want, put more into, let's say, our more modern way of like talking about tunneling and how we do this actual calculation in 2018, when basically Andreas and Frost and Schwarz looked again at this RG argument and understood you had to go at 2 loops to really make the integral convergent, so you can actually compute it analytically. And then basically understand that these 2-loop effects are kind of like choosing a specific scale. Also, that scale you kind of have to argue by some other way, because in this argument you're just arguing for what the mu and therefore R dependence should be, because of the fact that you want to cancel the leading log by log, you want to cancel the mu dependence coming from the running coupling, but also you're not actually computing the quantum corrections. And so what renormalization scale you choose is kind of like more comes out of the argument. But also, I should mention, you're not really capturing all of the effects. You're just capturing these logarithmic effects that you expect. And that's where we go to a second, if you want, parallel approach, despite the fact, of course, that these are tightly bounded to one another, which is, if we can, compute the quantum corrections directly. So, which, of course, if one does it completely, should then give you, among other things, also the correct renormalization scale dependence that you could have guessed from RG arguments. Now, let's say an intuitive way, I mean, first of all, here it's really important to somehow include the fact that quantum corrections break the classical scale invariance, therefore kill your zero mode. In order to do that, it means that somehow you also have to modify the zero mode equation. So you have to include some quantum correction at the level of fluctuations, namely at the level of the propagator. And so this calls clearly for setting up some sort of Schwinger-Dyson equation also for the propagator. And for this purpose, we choose, but is also not something that is necessarily very new, to work in the 2pi effective action that I will, so to particularly reducible effective action that I will introduce in a moment, because it's a very natural framework to generate the quantum equations of motion for 1 and 2-point functions simultaneously. As I said, it's not necessarily a super new idea. Already about 20 years ago, there are some first works, Berkner and Bettencourt, to my knowledge, the first one, of using the 2pi effective action for doing some calculations for vacuum decay. In this case, as far as I know, they were not really thinking about this IR problem for the standard model stability. They were rather interested in just trying to extend the usual instanton method to be able to include quantum correction through the use of 2pi. And this they did in the Hartree approximation that I will mention later on, and also in D = 2. And there are some later works of those years, but basically it wasn't something that picked up a lot, I think, at the time. But then a few years later, so Bjorn and Pete Millington in 2018, I mean, okay, this is, let's say, the end point of actually a couple more works that also were from those years. They were really thinking of the standard model stability issue, and despite the fact they didn't work in full 2pi, the inspiration was there. And we're trying to set up these similar Schwinger-Dyson equations. And now I should mention in the work that I'm basing this talk on from November, really what we did is set it fully in the language of 2PI and set up, let's say, the stage to generate these equations, understand the renormalization of all the quantities, as I will explain later on, without doing further approximations, so avoiding further approximations. Now, for this purpose, I also included a slide to try to be as clear as possible. So what do we do? I hope I convinced you in the sense that it's an interesting endeavor to try and include these quantum corrections explicitly. And if one wants to do so, the first step is at least setting up these systems of equations for the 1 and 2 point functions that go beyond the classical equations, right? So they must include basically interactions between the fluctuations in the bounce background. And this is what we do in our work and what I will try to describe in the rest of the talk. So we developed this language to systematically include quantum corrections. We work at one loop in the bounce background, which is effectively 2 loops, and explain how we compute and renormalize these self-energies, which are really complicated objects in position space. And also, we will work out, I will show you some numerical results, but these are for a very simplified 2-dimensional model. This is more like a proof of concept that the procedure is something that you can put on a computer and apply, but it's not yet the 4-dimensional scale invariant model. And this is also what I already say now for clarity, that this is something that we're still working on, because despite the fact that the concepts are all there are some numerical challenges that arise when trying to increase the number of dimensions, such as convergence. So it just becomes something of like one has to be more efficient in the numerics, let's say. And also, once you obtain the 1 and 2 point functions, the effective action is expressed in terms of those. So a priori, you can compute these determinants, you can compute these actions, you can compute the decay rate, but this we haven't done. Again, this, there are codes for this. This wasn't really the goal of this, at this stage, at least it wasn't our goal. Okay, so let's talk about 2PI effective actions. What is it? I'm assuming that not necessarily everyone is super familiar with it. So let's look at this for a moment. Now, you might know about the 1PI effective action. So how do we start? We define functional that is the generator, a generating functional for the connected endpoint functions. And we call it W as per usual. But instead of introducing just one current, which is J, the current such that we take derivatives, we generate for example, one derivative will generate the 1 point function. We also introduce a current R, that is the current generating connected 2 point functions. Okay, this in principle, no difference. We're allowed to do this. And we can also, of course, do a Legendre transform as per usual for the 1PI effective action. In the case of 2PI effective action, we have to do a double Legendre transform in which we transform both this function J into something that we call phi, and this function R into something that we call G. So at this stage, at this level, everything is very formal. We get a functional, which we call gamma 2PI, which is a functional of phi and G, which at the moment are completely independent functions. Phi a function of 1 variable and G a function of 2 variables. We can also expand it in loops. This is a long derivation. By the way, I should mention that this is, for example, an interesting introduction where all of this is also very well explained. And once we expand it in loops, we have, for example, the 3-level. The first contribution is just the 3-level action, which only depends on phi. And then we have some 1-loop terms that, G0 also depends on phi. This G0 is the 3-level propagator. So G0 to the -1 is simply the quadratic part of the action computed in the background of phi, often also maybe called S prime prime of phi. And we see that, for example, this expression coincides with the 1PI 1-loop effective action if G0 is equal to G. So we also already have a hint what G must be. I didn't call it G randomly. G must be the propagator of the theory eventually. And if we set it to be the 3-level propagator, we get indeed the 1PI 1-loop effective action. More generally, it is not just the 3-level propagator. And we have also an additional piece that starts at 2 loops. That is basically all of the other terms. Okay, this is a very nice framework to start generating equations of motion. So for example, if we take a variation of gamma to pi with respect to phi, we have the stationarity condition for phi, and we get an equation for phi being the background. And this is indeed the quantum equation of motion for the background, okay? So the three-level part, one loop part, where I define this pi g, which is basically nothing but a one loop surf energy, and then some other terms that start at two loop. The same we can do for g, so we ask for g to be a stationary function of the functional, and then we have this equation, 3.6, where I purposely called this object sigma, as we will see. It makes a lot of sense in a moment. Like this, maybe it's still not necessarily what you recognize as the Schwinger-Dyson equation. However, if we now, okay, I suppress the indices just to avoid a lot of integrals, but if we invert it and whatnot, we get 3.8. That representing it diagrammatically, we have G, in this case is my double line, is equal to G0, which is, remember, my three-level propagator. And then we have this convolution, so plus G0 convoluted with sigma, whatever this object is, it's a function of two variables, and then G. So now we understand a posteriori, indeed, sigma really should be the 1 pi self-energy, and G is the resonant propagator. Now, just to make sure we see it at this level, this is almost the usual Schwinger-Dyson equation. The main difference is that here the self-energy sigma is really computed with propagators G. And the reason is, we can go back one slide, you know, sigma is the variation of gamma 2 with respect to G, where gamma 2 was this object starting at two loops, and gamma 2 is only expressed in terms of phi and G. G0 never appears anywhere else in the action. So every time we have this sigma, it also will have a perturbative expansion, but all of the propagators that appear inside here are really the full G. So so this is kind of like a nonlinear equation rather than being the usual linear one. Okay, so let's look at what gamma 2 is. I mean, this is kind of justified a posteriori. Gamma 2 contains two pi vacuum diagrams, namely two partially reducible. It means you cut two lines, they're still connected. If we have a scalar theory with cubic quartic interaction, so the most general renormalizable scalar theory in 4 dimension, we have 3.9. And if we take a variation of it to find what sigma was, we basically cut one line here, and we have like a sum of diagrams that start as one loop. And we also have higher terms. Here they would be three loop that would lead to two loops contribution to get sigma. I'm neglecting them. I will always work at one loop, which is hard enough already, as we will see. And so as we can see, we have some diagram that is like, I will call it a tadpole in the future, because it only depends on one point. So it's like a local contribution to the self-energy. And we also have these bubbles that come from taking variation of these sometimes called sunrise diagrams. And these are bubbles, and they depend on 2 points, okay? And these little crosses, they are nothing but insertion of the background field phi. So for example, this would be a quartic vertex where 3 legs are attached to fluctuation, so to G, and 1 leg is attached to phi, being the background of the theory, okay? This means, exactly, so we have understood that basically from this formalism, we get a one loop corrected quantum equation of motion, and a sort of Schwinger-Dyson equation, where I mean sort of, because we're actually resumming a lot more loops than just the usual Schwinger-Dyson equation, since this propagator is always the exact propagator of the theory. Very well. So let's go into the next step, which is we have this language. Let's talk about vacuum decay. Let's call about bounces, and let's call about propagators in the bounce background. Now, equations, once I write them down in coordinates, I have 4.1 and 4.2. Despite the fact they look very simple, they're actually extremely intricate equations. At this level, they are the most general, almost the most general version. I guess now these are partial, because at this moment I haven't told you anything about the symmetry of my solutions. But also they are extremely nonlinear. I mean, V prime will be nonlinear. Sigma contains G, so this is also like nonlinear. They are integral. There's a convolution, and they're coupled. So this is pretty hopeless at this level. So let's simplify this a little bit. we use some symmetry of the problems. We know that we want to look for a OD invariant solution. This is always the case when we talk about zero temperature vacuum decay. We look for an OD, a rotationally symmetric instanton. This means not only that phi will only depend on the radius, but it also allows us to make some simplification for the two-point function. So here we come to 4.3. The two-point function, since we know that it should respect this symmetry, there should be some sort of like trivial dependence on let's say the angle, and then some between this x and y, and then some non-trivial dependence on the radii, so the distance between these x and y from the origin, being the origin basically the center of my instanton, of my bounds. And so I can make an ansatz in terms of hyperspherical harmonics. I'm still working in generic dimension. Kappa is just a useful shorthand because it will appear everywhere, which is d half minus 1. So this object is 1 in d equals 4, 0 in d equals 2, and so on. I have my hyperspherical harmonics that depend on the angle, and then I have some component, gj. This will be some basically the radial component of the Green's function that only depends on the radii. And importantly, it will, because of the spherical symmetry, this is really the heart of the spherical symmetry, these components will only depend on the total angular momentum J and will not depend on the individual values of L. And then I have this prefactor, it's just convenient representation. And the same I can do for the self-energy. So sigma, more generally, will be split into some local part, as I showed you, right? There's a tadpole that will multiply a delta function, because it doesn't really depend on 2 points, it only depends on 1. And then I have a non-local part that really actually depends on 2 points. But then when I write it up, but then this non-local part, I can do the same ansatz as for G. This is the case. The local part, by the way, because of the fact, I mean, I don't have to assume it, it also comes out of the calculation, but pi actually doesn't depend on x, as it should be, because of the spherical symmetry. It will only depend on the modulus of x. So we get finally at some equations that are in a form that is maybe more approachable. They look longer, but they're actually better. Well, first of all, I don't have, the main point is that I don't have partial differential equations anymore. Now these are ordinary differential equations. Well, okay, they're still in integral, so integral differential equations. But they are still nonlinear and they're still coupled. So let's look at them for a second. First of all, I have infinitely many of them, right? I have infinitely many j's that start from 0 and go to infinity. Also, they are coupled because pi here depends on g. So I cannot find phi without knowing g, but also I cannot find g without knowing phi, of course. And there's also a nonlinearity here because pi, as said, depends on g. So here it multiplies g, and sigma, of course, depends on g. So it multiplies g. And more importantly, pi and sigma j depend on all of the other g's simultaneously. So all of the gj's, they're also not decoupled. They depend all on one another. So of course, this is still a very, very hard problem, even numerically, which means we can only approach it self-consistently. And we also must truncate at some j max. So eventually we have to stop at some j. We cannot go all the way to infinity. But this is not a problem, as we are interested basically always in this sort of difference between what happens in the bounds and in the Volkswagen background. For example, in this ratio of determinants. And as j increases, so we kind of go in the deep UV, the Green's function will look more and more like the Volkswagen Green's function. This also is what should happen. So depending on the accuracy that you want to reach, you can choose at what j max to truncate your procedure. Now, I should mention at this stage that the Hartree approximation that I mentioned before, there is also a common approximation done in some 2pi context. It basically amounts to dropping this term. This is, for example, all the work that was done in these papers from 2003, 2004, where they were looking at vacuum decay in 2pi. They were always starting with the gamma 2 that I showed you before. For me, it contained this figure 8 diagram, but it also contained these sunrise diagrams. And the sunrise diagrams are the ones that eventually in this equation will come up as, will show up in this convolution. And then usually what the authors do in this work is basically say that they drop these diagrams to begin. Like at the very beginning, they just write gamma 2 this figure 8 diagram. They never consider other diagrams, so they never really write down an equation that contains an integral. Of course, this is a great simplification because integral differential equations are much harder than ordinary differential equations. However, we will avoid doing this simplification, as we will see. I should also mention, where does the idea of the arbitrary approximation come from? As far as I know, or I understand, when you look at large n systems, like for example, if you take an ON model with a lot of scalar field components, at large n, the arbitrary approximation is an exact approximation. Like at n equals infinity is exact in the sense that this term is usually suppressed at large n with respect to this term of the self-energy. And so this becomes like a good approximation, but of course for a single component scalar field, there's not really a reason why it should work. Okay, so what is my iterative, the self-consistent procedure that I was mentioning? So we start with we start with 3-level equations. Maybe I'll show them again. At 3 level, you're basically dropping pi from this term, you're dropping pi here, and you're dropping sigma here. So the equation for phi does not depend on g anymore, so you can just solve it. And the equation for g only depends on phi. And it's linear, right? Because the nonlinearity was contained inside the self-energies. So you have linear equation, and it's also, they're all decoupled, because once again, the coupling between different j's was also contained in pi and sigma. So they're all decoupled, they're all linear. So again, it's just a Green's function equation. In position space, it's complicated. Analytically, in general, there's no solution, but numerically this can be done. So that's what the first step is, starting from 3 level. But then you want to go beyond, right? So you start computing the self-energies. And this is a very actually non-trivial point, at least from an analytical standpoint, as I will show you in the next slides. I would say that also one of the main obstacles to developing this formalism and this procedure has long been really computing these things in position space and renormalizing them. But okay, assuming you have a way to do that, you compute pi and you compute sigma j's for a bunch of j's up to your j max, using whatever you found in the previous step. So in this case, the trivial one for the background and for the propagator. And then you go and find again your solution, right? So you go to the quantum equation of motion now, and you find again the background, you find again the propagators, having basically used the self-energies as computed with the previous propagators and the previous background. So you also linearize, if you want, the equation. And now you check basically for some convergence condition that you might require, that you decide to require. It could be, for example, that basically you want to check whether the g and the phi that you're finding now have changed a lot compared to previously. And if they have changed and they keep change more than you are willing to allow, so more than your threshold, you both go back to this box. You compute once again the self-energies with what you now found as background and g, as phi and g. You compute once again now phi and g at the next iteration step. Go back to your convergence check and repeat this. Once you are happy that you see that indeed, maybe for the last, 2-3 iterations, phi and g have not really changed much, you can get out of the loop. And finally, you can say, I found a solution. And I have bounds phi, and I have the propagator g. And these are really solving the quantum equation of motion at one loop. So they're effectively resumming an infinite amount of loop contributions inside them. Which also means that the fluctuations encoded by the propagator now are the fluctuations in the quantum theory. Okay, so for example, when we talk about the classical scale invariant system, at this stage, G will not contain a dilatational zero mode anymore, because that object is not a zero mode of the quantum theory. It will be gapped. Okay, very good. So let's keep going. I mean, also, this is still very general and it's applied to basically any model you can treat this way, like with the single scalar, any dimension as well. I haven't reduced it yet to our simplified example in the numerics. As I told you, what becomes pretty hard is actually computing the self-energies. So for this example, I'm taking once again the most general renormalizable scalar theory in 4D. So phi cube plus phi 4 with some couplings, which by the way can be set to 0 if convenient. We can, for example, set m to 0, g to 0, and then we are back at the classical scale invariant case if lambda is negative. So the local contribution to the self-energy, which I call tadpole, is this object. So basically, the divergence is encoded in the fact that we are in the coincident limit of G. And now in momentum space, if you write this thing, you're going to get the usual tadpole integral. It's just the integral over the form momentum of a single propagator. So in Euclidean signature, it's going to be 1 over p squared plus m squared. But we cannot work in momentum space, right? That's the whole point. We don't have translational invariance. So the best we can do is work in angular momentum space. And instead of integrals, we're going to have sums. So when I write this out, I get 4.10. Instead of having the integral, right, over I would maybe use my, I don't know, in the form momentum integral, I would eventually just have to integrate over the modulus of p. The angular parts are kind of trivial. And in a sense, this is similar. So what we get, instead of an integral over the modulus of the form momentum, I get an integral, well, I get a sum, sorry, over the total angular momentum. Okay, so once I can use some identity to resolve these sums over L, and I get some expression. Again, remember that kappa is simply a factor that depends on the dimension. So it's d half minus 1. And so what I see here is indeed that I have this coincident function. This is in general finite. The infinity comes out of the fact that I sum all the way to j to infinity. So depending on the dimension, this object is going to be more or less divergent, but it is going to be divergent in any dimension. And to understand the divergence that I find, and I need to because I want to renormalize this, what I can do is I can ask myself, what is the behavior of G when J is very, very large? Once again, this is a trivial problem when working in momentum space, but because of the fact of the breaking of translational invariance and because of working in position space, everything is really hard, even computing a single one-loop diagram, the simplest one-loop diagram. So if I want to know what's the large J behavior of G, I can use WKB. This is not really obvious, and there's a long discussion in our paper about this because it took me a long time to understand whether this was allowed or not. And the reason is the integral kind of spoils your procedure. And if the integral is relevant for large J in your integral differential equation, you cannot use WKB, and then you're screwed. Fortunately, however, you can indeed argue why the integral does not matter for large J. And so you can drop it and use WKB on what is left, because then you have an ordinary differential equation and you can find the Green's function in the WKB approximation. And this is, for example, in the coincident limit, it becomes very simple. I won't show the solution in the non-coincident limit. But in the coincident limit, we have this very simple expression plus higher orders that are not relevant for this case. And we see that if we plug them in, indeed the one, sorry, maybe I should show here, the 1 over j, okay, this is a ratio of gamma functions, right? At large j, it will go like, well, it depends on kappa. In d equals 4, kappa is 1, so this is gamma j plus 2 over gamma j plus 1 is just j plus 1. This is also j plus 1, so at large j, you have like j plus 1 squared, and gj goes as 1 over j plus 1. So you really have a quadratic divergence, as you should expect. This is divergences don't really care about your background, so you should have the same quadratic divergence that you find in a flat background. Now, to regularize our sum, then okay, now when I want to regularize, since eventually I want to regularize in DIMREG to find a result that is more similar to what I know from momentum space, I have to pick up a dimension. So far it was all generic dimension. Now I'm saying, okay, let's do this in d equals 4 minus 2 epsilon. And in 4 minus 2 epsilon, kappa is 1 over 1 minus epsilon. And so I can write my sum. So I get rid of the WKB part so that this sum is now finite. I just choose enough orders in GJ WKB so that this sum is finite. In d equals 4 minus 2 epsilon, it's enough to get rid of this term and this term. And then the rest will not be relevant. So once you subtract the first and the second term in the WKB expansion, this sum is finite and you can set epsilon to 0. So in this first term, epsilon is 0. And then I have to add it again, right? So I subtract and add the same quantity. But the good thing is that now I add it again, and this is like a nice function. I have an analytic expression for it, which means that I can do the sum explicitly, analytically, in kappa equals 1 minus epsilon, so in D equals 4 minus 2 epsilon, and find the result, which is given in 4.12, in which I have a fully finite result, a fully finite sum, which is what I want to handle numerically, right? Because numerically, I don't want to have to compute sums that explode, and I have a explicitly normalized, and then I have a regularized object. And now I can use my favorite randomization scheme. I mean, in MS bar, for example, I simply have to drop the pole. I should mention, by the way, it's important. For example, it's nice that you can see that the leading order you recover the usual divergence. So if you were to compute this object in momentum space, you get m squared over 16 pi squared epsilon here, and you get the same in momentum space. So this is a nice double check. It means that after your whole procedure, you're actually reproducing what you expect, and you know from momentum space, which has to happen because you know the counter terms don't care of your background. Now I said a leading order because, of course, the fact that we're using a resummed mask that already resums infinite loops makes also the fact that the one loop counter term, of course, don't fully normalize this object. We're gonna need also like some higher order contributions. But at leading order, you can check explicitly that this goes back to the usual thing you expect. And then eventually, okay, we don't really want to work in MS bar. We work in what we call the an on-shell scheme, but basically we kind of define a scheme such that the false vacuum is always the false vacuum. So you want to define a scheme so that when including quantum corrections, the false vacuum is not shifted around. And so you just define it so that, for example, this coincident Green's function is exactly 0 if I'm working in the false vacuum background. So for example, in this case, if I set G in the false vacuum, G would be G0, so these two drop out. M squared phi would be M squared, and so this drops out, and this is all 0, right? That's it. Very good. So this I went into great detail. I won't do the same for the bubble, although this is definitely, let's say, the most technical and challenging part, and in a sense also the more interesting, the more interesting result maybe of our work. And basically, the very hard part is that you start now with the square of the Green's function at different points, and you somehow have to square this expression that I write here and write it in a way as in 4.15 as the last line. And this is going to be very intricate because here you have products of, here I use some identity of the hyperspherical harmonics to write it in terms of Gegenbauer polynomials. And then you have to use some product rules of Gegenbauer polynomials that you're going to find on your favorite obscure math paper in the internet. But okay, you check, of course, whether these are correct. And then you find after long work, you can maybe hopefully get to something like in 4.15, which you do. But of course, I'm hiding everything into sigma j. Sigma j is really the monster here. I won't write down what it is because it would take the whole slide, and I don't think it would be necessarily very enlightening. But the interesting part is that basically what you find is a structure that kind of looks familiar. So you have a lot of sums. You don't have only one sum. You have a lot of like 2 or 3, depending on the terms, 2 or 3 inner sums inside sigma j. But basically, once you kind of understand the structure, it looks like this. It contains 2 g's, which makes sense, right? Because we started with a g squared, but computed a different angular momentum. And so now J kind of plays the role of an external angular momentum. And now we have what I will let me call a loop sum over the angular momentum. And the 2 G's computed at Q and Q plus J. And this resembles a lot, indeed, what you would find, for example, if you compute this thing in flat space in the momentum representation. Because the same object you can write in a line, and what you're gonna find is that the self-energy with external momentum P is going to be an integral over the loop momentum, let's say kappa, and then you have the 2 propagators computed for kappa and kappa plus P. So it's really nice. The structure is exactly the same. And also, if you analyze the divergent part, which is what we care about for normalization, you get something as in 4.16. Why is it cool? So it's cool because, first of all, R minus is the minimum between these two. R greater is the maximum. So this means this object is always less than 1. less or equal. If it's less than 1, this is exponentially suppressed, and this is fully convergent. But if it's equal to 1, it's not, right? If it's equal to 1, this thing, the exponential suppression is not there anymore, and then the 1 wins, this object diverges again. So you still have a divergence inside here. But you have a very peculiar divergence. So you have a divergence that only pops out if Rx equals Ry. But this is indeed what you want, right? You want this because it means that all of the divergence is encoded in basically the coincident limit, so in a delta function. So it's a local divergence. And again, this is QFT. We should always only have local divergences. We should recover the same divergence we would have computed if we had computed this object in flat space. And indeed, one can show that in a distributional sense, you can compute these sums, again, like as distributions, so in a sort of like weak limit, if you want. And you can compute explicitly. You can extract, indeed, the delta function behavior of this object, and you can see that it multiplies a 1 over epsilon in 4 minus 2 epsilon dimension, which means that, indeed, everything can be renormalized by local counter terms. And I'm not showing it here, but also for the bubble, which is a lot more complicated and the calculation is a lot longer, you can, at the end of the day, extract the divergence and check that you get exactly the same divergence with exactly the same prefactors and factors of pi and whatnot that you would have found if you had computed it in momentum space, which is a very nice check at the end of the day, because this is a very long calculation and a lot of factors of 2 could have gone wrong down the road. Very well. So I went in a little bit of the technical details because I think it's good to do justice to some of the harder parts. But after you have all of these, you can go back to the scheme that I showed you with the nice arrows of all of your machinery, write a lot of lines of code, depending on how good you are at programming, more or less, and try to run this. Now, we decided to work the d equals 2 because we started working also in d equals 4, and this is still something that is going on. But it just so happens that after also looking around in self-consistent procedures, that in a lot of fields of physics is something rather explored, that as you go up in dimension, it's kind of to be expected. The convergence takes a lot more longer. So I guess we tuned it down because it was also our first time kind of working this out numerically, and it was a good first step to at least do it for some case where we can see, okay, it works, it converges in a humanly long time on my computer. But eventually, of course, this must be generalized. I show some. For some choice of parameters, some result. I mean, for this choice, we work at rather weak coupling because we want to have a very good control over the quantum corrections. And we see this is a cubic plus quartic interaction. In a 2-dimensional case, we see that the bounce is basically unaffected, which is not surprising because we're working at rather weak coupling. So the effect on the classical bounce is small. I just highlight that there is an order 1 difference between whether we do a hard 3 or 2pi, which in a sense is like the whole point, I think, also of our numerics. If there's a conclusion is also that, okay, we can argue it qualitatively, but also quantitatively, that generally this hard 3 approximation that people in the community of like these 2pi approaches do for this case is definitely not a good approximation. The difference is big. Even at the level of the self-energies, this can be checked explicitly. So this is, for example, the tadpole self-energy compared to kind of like the local limit, so the coincident limit of the bubble self-energy. And I mean, okay, it's hard to compare like a 2D function with a 1D function. But if we just look at the peaks also, we can see that there's no parametric, difference. Actually, here it even seems that the bubble is more important, which once again tells us this local approximation, this R3 approximation is not really viable. But I think most importantly, it kind of shows that we have a working code. This can indeed be done on a computer, and by scaling it up, I'm confident that pretty soon it's going to be applicable also to the 4D case, which is the case of interest. And so this brings me to my conclusion. So we learned a few things. So we can work with the effective action, and it kind of makes sense to maybe choose to work into PI. There's definitely other ways to include quantum corrections in the fluctuations. We choose this as a convenient framework to generate equations of motion, but of course, it's not the only way. The equations are very hard. However, if we use spherical symmetry and smart identities for our special functions, plus a lot of manipulations on the sum, we can indeed write everything in terms of like renormalized self-energies, even in the non-local parts, and extract the full local divergence, renormalize it analytically so that numerically we always only have to handle finite quantities. And this is highly non-trivial, but very nice, because once this is set up, again, it becomes only a technical issue of like putting it on a computer and running it, and not a conceptual one anymore. And also by doing our simplified numerics, we can at least give a quantitative check that indeed, once this works, two, dropping these convolution integrals, even though very tempting, because we would avoid a lot of difficulties, is not a reasonable thing to do. And our next steps, finally, is indeed, as I said, to scale this up and use everything we developed to now work in 4D, especially to analyze the scaling variant theory. And then, I mean, once this is done, we can also compute the decay rate for the theory and compare it maybe to previous approaches. And this leads me to my end. So thank you very much for your attention.
Thank you very much, Matthias. Yeah, for a very nice talk and very clear. It was nice to see a lot of the details that you showed there. I felt like it was very clear to follow. But yeah, now there is some time for questions. If anyone has any questions, please raise your hand in the chat, or if you can't find that, just unmute yourself and ask a question. Bogomila.
Hi. Sorry if there is some background. I'm at the conference. So I wanted to ask you, what is the expected gain of this approach when you compute the nucleation rate? Because my understanding is that you basically improve on the scalar prefactor of the decay rate, right? By resumming more stuff into this. And if you do it in one PI, this factor is usually rather small. So is there something specific you expect it will help for?
Yes. Okay. Thank you very much for the question. That's a very good point. I might have not made it clear enough. So of course, at the level of a generic theory, where we don't have, for example, the classical scaling variance thing or so on, this is basically only improving some accuracy. That indeed, a priori, it's not very needed. It would already be amazing if if we can observe some nucleation event at zero temperature in some system, and it would I think the uncertainty will be so big that even the prefactor it's questionable. This is only really useful if we have some system, like for example the classical scaling variant one, but there are other examples where basically the quantum effects are, in the case of the classical scaling variants, a lot more important at the level of the fluctuations than the tree level. Because at tree level, we have, for example, this zero mode, this dilatational zero mode, that would blow up. It would give us this IR divergence. But we know that this is not there. If we do this thing, quantum, if we were able to do, I don't know, the full quantum effective action thing, we wouldn't see this. So this is really only needed when sometimes in some of the work, people use the following words, when basically the one loop becomes more important at the tree level. And this is the case, for example, in the presence of this classical symmetry, is also the case in if another interesting example that I think was explored in some papers from 2015 also by Bjorn is if your minimum is only generated by radiative corrections or quantum corrections, that's also another case, because if you look at tree level, you don't even have the decay. So it's only in these specific cases that it's interesting. And I try to motivate it with the standard model stability to just say that there's at least one phenomenological model where, well, I think there's some interest in this. I hope this answers the doubt.
Yes, thanks. So, well, my understanding somehow is that if you generate your minimum, let's say, via quantum corrections, it just means your one loop is actually belongs to the leading order, actually. So then you maybe reorganize your perturbative expansion, and you can also account for this.
I mean, I know. Yes, I guess. I mean, if there's another way to do this in the case, for example, of spontaneous symmetry of Coleman-Weinberg basically generated minimum, I guess this is a way, yes. I mean, I was just explaining like this way, for example, for in the case of the classical scale invariant case, how one can include the quantum corrections explicitly.
Okay, thanks a lot. I like the talk a lot. Thanks.
Thank you.
We have a couple more questions. Let's move on to Lorenzo.
Hello, can you guys hear me?
Yes, yes.
Yeah, first, Matthias, thanks a lot. I really enjoyed your talk. I have two questions, if I'm allowed. One is very quick. In the last part that you showed, for the two decays, did I understand correctly that the model you looked at is phi squared plus phi cubed plus phi to the fourth?
Yes, yes.
Okay, good. The second question is, so if you go back to the equal 4, so your motivation started with this scale invariance, right? But now, if I understand correctly, the techniques you developed only work for scalar fluctuations, no? You go to the 2pi for scalars, right?
Yes, we brought it down for scalars, yes.
But now, if you have a classical scale invariance with phi to the fourth, and you even go to through loops and whatnot, doesn't, I mean, there is no, the running of lambda has no minimum, nowhere. So there is no bounds. So, I mean, for instance, now in the paper also you quoted by Andreasen and company, they state this very clearly, The reason why in the standard model this works is that at some scale mu, of the order 10 to the 17 GeV, there is a minimum because the beta function goes to 0. But this is due to the other fluctuations. You need the fermions and the gauge bosons. If you don't have that, what are you doing?
So, I think that's a very interesting point. Thank you. So I understand where they're coming from, and they need the existence of this minimum to basically set what they expect the critical scale of the instanton to be, so that they can localize the integral. However, I will say, so two things to that. So so first of all, the question of the decay rate, it's a well-posed question, even if the potential is unbounded from below. I mean, even in just the lambda phi 4, we can find an instanton analytically, right? The Fubini-Lipatov instanton at classical level, which describe the decay of this metastable state that sits on top of the hill. So I don't think that the lack of an absolute minimum makes the question necessarily ill-defined. At the same time, because of this, right? If I forget about the fact that other fields exist, in just a scalar field with phi 4, the quantum effects should break scale invariance, which means that they should localize, like you should be able to find a critical scale for the instanton, even if there's no absolute minimum, because there's no scale invariance really in the theory. And so what I would expect to find is, by analyzing the scale invariant case in the equals 4, that even in the absence of other fields, there should be some maybe soft, but definitely induced R dependence. So like this radius inside the integrand.
But this confuses me because, I mean, I agree that at quantum level you break scale invariance even in this case, but if there is no minimum, then there is no scale in your problem. What dictates the scale anymore? So, for instance, I think that my interpretation at that point would be that now you have, I mean, if you have lambda phi to the fourth corrected to one loop, but you only have scalars, maybe the interpretation is that now it's true that at 3 level you have the Fubini-Lipatov bounds. But maybe what happens is it's like, maybe one way I can think about this is, let me compute the one loop effective potential. Now this becomes even steeper than phi to the fourth. So what actually happens, I mean, technically, I think if you do the computation, what you find, and maybe I suspect this could be a reason why your d equal 4 calculation numerically is not converging even. What it could be is that the actual rate that you're trying to compute formally diverges. And I wonder if an interpretation of that is that actually now you're not longer tunneling, but you're really classically rolling down the phi to the fourth or steeper potential.
But
maybe this is wrong what I'm saying, but if you don't have actually a minimum of lambda, which in the standard model you do, only with scalars without the minimum, it's not obvious to me that this is a sensible calculation.
That's a very good point. I don't think it's necessarily an obvious thing. And I definitely need to think more about it. I also don't want to steal all of the time for the questions, but I think just to maybe add something to that, No, I think it's a thing to think about. I don't necessarily. I'm not sure also of this interpretation that you're just classically rolling down.
Yeah, I could be wrong. Just
Okay,
I'm
because at
thinking
the
of
level, yeah, no, because at the level of just the way this decay rate is written, I wonder whether, okay, if your interpretation is correct, I wonder what would diverge then, right? Like the determinant, it's something you're going to compute. Maybe the action, maybe you're suggesting maybe the action of the solution can like explode.
No, I mean,
and there's
I would expect the rate to diverge, no, the full rate to diverge, and maybe one interpretation is that, but maybe I'm wrong.
I mean, it's a good point, and I will think about it more. But I think it's definitely something to keep in mind.
But that's it. Thank you. I found your talk very clear. I really enjoyed it.
Thank you. Thank you. So, Oliver, you are muted,
sorry.
but I guess.
Yeah, there we go.
Yeah,
Thank you again. So there is one more question by Alexander, but I'm afraid I am going to have to leave now. But let me just say thank you, and let's stop there unless anyone wants. So Alexander and Matthias, if you're happy to stay, or anyone else who wants to continue discussing. Miha, if you're happy to leave the room open for a bit for people to discuss.
Okay, I'll stop recording.